So in this video, we will be solving part 3 of the homework here, where the situation is that we have a cylindrical barrel of radius r and length L laying on its side. It is oriented such that the barrel can roll. So when the fluid level in the barrel is h, calculate the horizontal pressure force on one cylindrical end cap and one cylindrical half. So I have already made a little diagram of the situation. To start off, this is our cylinder here with a height of h, length of L, and a radius of r. We have our liquid here, which is exerting a force on our cylindrical half here, and then the circular end caps as well. And then I also have a horizontal or really vertical profile view of the cylinder as well. This is the liquid, and also at length L. As you notice, we have this little amount of height dh, which basically that is signifying that depending where you are, at what distance you are below the liquid, it will exert a different amount of pressure. So basically we are calling the height of our liquid 0, and then wherever we're going to is going to end up being h when we are using an integral. So to start off, we're going to be looking for the force on one cylindrical half or side. So that's going to start off by just using our basic equation for pressure, which is pressure equals force over a given area. So then that means that the force on one side is equal to pressure times the differential of the area, and then we can substitute in for our pressure, our basic equation for pressure of a fluid, which is rho g h. So I actually made a mistake here. This should be height h as it states in the problem. The liquid is at height h. So now what we can do is we can expand this dA into L times dH. And then now what we want to do is actually integrate. And basically what that will be doing is combining all of our little chunks here. And we're going to want that from 0 to our height h. So now to take that integral, we are going to put all the constants in front, rho, g, and o, and then the integral from 0 to h dh. And put dummy variables in there. And then, so the integral of this will be 1/2 h squared. So then if you plug in the 0 to that term will just go away. And we will end up with the force on one cylindrical half or side will equal rho g L h squared over 2. So that will be the force on one cylindrical half or side of this cylinder. So now we're going to start the second part of this problem, where we will be trying to find the force on one circular end cap of this cylinder. So I copied down our answer for the first part up here, and as you can see, I made a diagram of this new second situation of the circular end cap. So we still have that liquid at height h, we have the radius r, and then I've kind of labeled right here an angle theta, and that angle theta is going to be creating a side here that we're going to call r sine theta, and a side here that we're going to call r cosine theta. And then I've also labeled this distance here as h minus r. As you can see, it's just h, and then subtracting this r. And then I've labeled this angle theta 1. So we can actually use this to solve for theta 1. I'm going to put that down here. We can say that theta 1 is equal to sine inverse of opposite over hypotenuse sine inverse of h minus r over r. And then as you can see, I have copied down some equations that we used in the first part as well. Again, our pressure in this situation is equal to rho gh for the liquid. And then again, we knew that our pressure was equal to force over area. So I already rearranged that equation, so force is equal to pressure times the differential of the area. And then again, we will be taking the integral of that as well. So now what we need to figure out is our dA will be different in this situation. It's actually going to be the width here times dH. So those little slivers are actually going to be the width instead of the length. If you can kind of understand that spatially. So it would be the width W dH instead of L dH from before. So now we can also substitute this in. So we'll get that the force, and I'm just going to call this force 2, will equal, again we'll have that integral rho gh times the width dh. And one more thing to remember is that our height will be changing in this situation as that cylinder is rolling. So we're going to need a equation for h as well. And that's just going to equal, again, based on our angle here, theta, is going to be r plus that height here that we already determined as r sine theta. That will be our h. It will be r plus that side that we already figured out to be r sine theta. Or sine theta. So now we can start simplifying this equation up here. Or not really simplifying, just solving this equation up here. So we need to keep in mind that we are doing a semicircle here. So it's going to end up being 2 rho g, the constants out front, and then our integral. And our integral is going to be from theta 1 up here to down here in negative pi over 2. And then we can plug in our h equation, which we have down here as r plus r sine theta and then our w, or width, is just going to be this here squared, which will be r squared cosine squared theta, and then our dh. So now what we will do is multiply this out and factor out our r to the third. So it'll end up being 2 rho g r to the third integral from theta 1 to pi over 2. So I'm actually going to end up splitting these up. So our first one will just be cosine squared theta d theta. And then our second one will be sine theta cosine squared theta d theta. So again, I messed this up here. Should be d theta. So if you don't see how we got to that, we just multiplied this by both of these and then factored out r to the third. That's how we got our cosine squared theta, and then our cosine squared times sine theta. So now we will be using Wolfram Alpha to solve these integrals. I've already inputted the first one here, or cosine squared theta d theta. So I'm going to start by writing that down. So our F2 will equal, again, our constants staying the same. Now it's going to be a pretty large equation here. So we're going to have 1/2 theta plus sine theta cosine theta. Yep. Evaluated still from theta 1 to negative pi over 2. And now for our second one, we just need to add a sine theta here. So it looks like this one's actually simpler. Negative 1/3 cosine cubed theta. Yes. Evaluated from theta 1 to negative pi over 2. And I'm going to finish this off here. Like so now using this equation here for our theta 1, we can also tell that sine of theta 1 is going to equal h minus r over r. And then using a trig identity, we know that cosine of theta 1 will equal the square root of 1 minus sine squared theta 1. And if we just plug this in, we will get that cosine theta 1 is equal to the square root of r squared minus h minus r squared all over r. So that's going to help us evaluate this here. So again, to start off, we're going to have the force 2 is equal to, and we're still just going to have these constants here, 2 rho g r to the third, and then in the brackets, negative pi over 4 minus 1/2, and then our inverse sine of h minus r over r minus h minus r square root 2 hr minus h squared over 2 r squared minus 2 h r minus h squared to the 3/2 over 3 r to the third. And this will be our final equation for the pressure force on one cylinder or one circular end cap here. So again, this will be our pressure force on one circular end cap, and then up here will be our pressure force on one cylindrical half or side. And again, that's 1/2 rho g L h squared.